Welcome students to online classes of mathematics for class 9th. In this video we are going to study the chapter number 9, which is areas of parallelogram and triangles of NCERT textbook, and we will be looking at the exercise 9.1. This one is the session number 1 for this particular chapter. Myself Deepak Gautam, DGT Mathematics in Kendriya Vidyalaya Sangathan. So let's start with our today's class. The chapter number 9, areas of parallelogram and triangle, is divided into total 3 subtopics which are listed here, in which the first one is the figures on the same base and between the same parallel, and the second is the parallelograms on the same base and between the same parallel, while third is the triangles on the same base and between the same parallel. Okay, so in first we have figures which are on the same base and between the same parallel, then we have parallelogram which are on the same base and between the same parallel, and then we have triangles which are on the same base and between the same parallel. Okay, so today we will be looking at the figures which are on the same base and between the same parallel. Okay, so before coming to the topic, let's first recall some basic terms and the definition involved in this chapter. So first one is the planar region. Planar region is the part of plane enclosed by a simple closed figure is called planar region. Okay, so a part of plane which is enclosed by a simple lines is called a planar region. For example, you can see here, suppose this white sheet is a planar region. In this I have enclosed an area by this line. Okay, so this region is now called the planar region. Okay, this entire white sheet is a plane and this enclosed area is called planar region. Okay, that's what this definition is. The part of the plane enclosed by a simple closed figure is called planar region. Okay, next is the area. The magnitude or the measure of this planar region is called the area. Magnitude means numerical value. Okay, numerical value. Okay, the magnitude or the measure of this planar region is called its area, which is, let's see this figure again. Suppose the length of this figure here is 4 centimeter and here width is 3 centimeter. Okay, so when you multiply this 4 into 3, you will get it as 12 centimeter square, which is the amount of space or the area enclosed by this planar region. Okay, so this is called its area. This is the magnitude or the measurement for this planar region. Okay, so simply area is the magnitude or the measure of this planar region is called area. Okay, next we have congruent figure, which you have already studied in chapter number 7, triangles. It's with this says two figures are called congruent if they have same shape and same size. Okay, two figures are called congruent if they have same shape and same size. For example, we have these two figure A and figure B. These two are having a same shape. As you can see, both are trapezium, and the size of both one is exactly similar or equal. Okay, that means once you place this figure A over the figure B, they will completely cover each other. Okay, so such two figures are called congruent figures, the figure which have same shape and same size. Okay, so if two figures A and B are congruent, they must have equal area also. Okay, since these two figures are congruent, that means their shape and the size are exactly equal or similar. Okay, then in that case the area enclosed by each has to be equal. Okay, so if figure A and figure B are congruent, they must have equal area also. Okay, that means the area of these two figure A and figure B will also be equal. Okay, that is, if A and B are two congruent figure, then the area of figure A has to be equals to area of figure B. Okay, we denote the area of figure A by the symbol AR inside bracket capital A, and the area of figure B as AR, and inside the bracket we write the capital letter B. Okay, so this ARB represent the area of figure A, and this ARB represent the area of figure B, or we can write it as the ARA is equals to ARB, that is area of figure A is equals to area of figure B. Okay, that's how we read this. So what you have to understand here is that congruent figures are figures which have same size and the same shape. Okay, the figure which have same shape and same size are called congruent figure. Okay, and if two figure are congruent, then their area has to be equal. Okay, we can write this as area of figure A is equals to area of figure B, or in short we can write this as AR equals to AR A is equals to AR B. Okay, now next is, you can see this figure, this entire figure T is having a shape like this. Okay, in this shape we have divided into two region. First is this region P and second is region Q. Okay, so the planar region formed by figure T is made up of two planar region formed by P and Q. Okay, then the area of this planar region T will be equal to the sum of the area of P and sum plus the area of Q. Okay, so if you wish to find the area of this planar region T, that will be equals to the sum of the area of planar region P and planar region Q. Okay, if you add the area of P and Q, you will get the area of T. Okay, now next topic is figures on the same base and between the same parallel. Okay, which is the first topic of this chapter. Now look at this figure. In the figure first, what we have here is we have a trapezium which is A, B, C and D, and we have a parallelogram which is C, D, E and F. You will find that the trapezium A, B, C, D and parallelogram C, D, E, F, they are sharing a common side. That is, this side DC is common for both the figure. So that means they are having a common base, or you can say same base. Okay, both the trapezium, this one and this parallelogram, are sharing a common line or common side, so that is the common base for the two figure. Similarly, in the second figure you can see that here we have two parallelogram PQRS and parallelogram MNRS. In these two parallelograms you will find that they are sharing a common side, that is the SR. So the common base here is, or you can say same base here is SR, while here it was DC. Okay, in the third figure now we are having two triangles. Again the triangle ABC and triangle DBC are sharing a common side which is BC. So the same base here is BC. Okay, in similar way now we have a parallelogram and a triangle. Again they are sharing a common side which is DC. So the common base here is, or you can write same base here is DC. Okay, so you will look at the two figure, you will find that each pair of figure is sharing a common edge or a common side. Okay, and that side is called the same base for each figure. Okay, now look at the following figures. In this figure you will not only find that they are sharing a common base, but they are also lying between the same parallel. Okay, which means here we have a trapezium which is A, B, C and D, and a parallelogram C, D, E and F. Okay, so in this trapezium and a parallelogram you will first see that these two are sharing a common base which is DC. So their common base here is DC, while you will find that if you extend these line, they are lying between the same parallel lines. Okay, so the same parallel here is this. Always while you write parallel line you will mention only the end point. So the first parallel line is AF, which is parallel to DC. Okay, now look at the second figure, this one. Here we have two parallelogram. First one is P, Q, R and S. Second is M, N, R and S. In this the common base here is SR, and they are again lying between the same parallel lines. Okay, if you extend this line you will see that the all four vertex or the all four vertices of these parallelogram are lying on these parallel line. Okay, so the base here is SR and the common line parallel lines are PN is parallel to SR. Okay, in similar way in the figure 3 you will see that they are sharing a common base which is BC, and they're lying between the same parallel line BC and AD. Okay, so the base common base here is BC, and the parallel lines are AD parallel to BC. Okay, when you extend the two line, you will find that the vertices of both the triangle are lying on this parallel line. Okay, in similar way, in the parallelogram A, B, C and D and triangle P, C, D, you will find that they are having a common base which is DC, and the parallel lines here are, let's extend this line, you will find that all the vertices are lying on this line. So the parallel lines are AB, not AB, AP. Okay, you will write the endpoints. AP is parallel to DC. Okay, so in this figure you will find that the figure are standing on the same base, and they are also lying between the same parallel lines. Okay, so based on this, we have exercise 9.1 where you have to just locate the common base and the common parallel lines for the given figures. Okay, so question number 1 of exercise 9.1 is, which of the following figure lie on the same base and between the same parallel? In such case, write the common base and the two parallel lines. Okay, so let's write as answer number 1 part first. Okay, so in this first figure you will see this, we have a trapezium which is A, B, C and D, and we have a triangle P, C, D. Okay, you will see that this trapezium and a triangle, they are standing on a same base which is DC. Okay, so the same base here is DC, and they are lying between the same parallel line. If you extend these two lines, you will find that these are the common parallel line for both the figures. So parallel lines here are that AB is parallel to DC. Okay, let's see the part second. In the second figure, now we have a trapezium and a parallelogram. In this trapezium, they are sharing a common base which is SR, but as you can see, if you extend this line as the parallel line, the vertices M or N are not lying on this line. That means they are not lying on the same base, but not between the same parallel lines. Okay, so here we have only same base which is SR, but they are not lying on the common parallel line. Okay, now let's see the part third. We have this figure. Now we are having a parallelogram which is P, Q, R and S, and we are having a triangle TQR. Okay, for the parallelogram PQRS and triangle TQR, common base here is this QR, and if you extend this line, you will find that all the vertices are lying on this parallel line. Okay, so the common base here is QR, and they are lying between the same parallel line. That is, parallel lines are PS is parallel to QR. Okay, that's the answer of the figure 3. Okay, now let's see the next figures. We have figure 4. In this one, you will find that we have a parallelogram A, B, C and D, and we are having a triangle RPQ, or you can say PQR. So if you mark the base of the triangle, it is not the same as the base of the parallelogram ABCD. Okay, because we have some portion here and here also, so they are not on the same base, but they are between the same parallel line. Okay, if you extend this line, you will find that they are between the same parallel line. Okay, so the answer of part 4 is, there is no common base, but parallel lines here are that AD is parallel to BC. Okay, now let's see the figure number 5. Here we have two trapezium. Okay, so first is trapezium A, B, C, D. Second one is A, B, Q, D. Okay, or you can also see it as one trapezium A, B, C, D. Okay, A, B, C, D, or ABQD. Okay, so you can have here two trapezium, or you can say that we have two parallelogram. Okay, in both the case we are having a common base which is AD. So for this figure, common base or the same base here is AD, and the parallel lines here are, if you extend this line and this line, you will see that all the vertices are lying on this line. So AD is parallel to PQ. Okay, now let's look at the last figure, which is figure number 6. Here we are having two parallelogram. First is A, B, C, D, and second is P, Q, R, S. Again, if you mark the base for the parallelogram ABCD, there is some portion left here and on the both side. Okay, so they are not on the same base, but if you extend this line, you will find that all the vertices lying on these parallel lines. So there is no common base, but we have parallel lines. Okay, same parallel line, which is in this case is PQ is parallel to SR. Okay, so that's how you have to write their answers. So there are only three figures, figure 5, figure 3 and 1, which are on the same base and between the same parallel, while these three are not on the same base and between the same parallel. Okay, so answer for this one is figure 1, 3 and 5 are on the same base and between the same parallel, and for them the common bases are written here. Okay, so that's the answer of exercise 9.1 of chapter 9. Okay, now moving ahead, we will do some theorem also before the exercise 9.2. So this is our subtopic number 2 from the chapter number 9, which is the parallelograms on the same base and between the same parallel. Okay, so here we are going to deal with the parallelograms which are on the same base and between the same parallel. Earlier we had the figures on the same base and between the same parallel. Okay, so there we are having the trapezium or a parallelogram or a triangle. Okay, pair of triangle or pair of trapezium or a pair of parallelogram. But here we will have only the parallelograms which will be on the same base and between the same parallel. Okay, so based on this we have a theorem, which is theorem 9.1. The statement of the theorem is the parallelograms on the same base and between the same parallel are equal in area, which means if we have two parallelograms which are on the same base and lying between the same parallel line, then the area of the two parallelogram is equal. Okay, so whenever we have a pair of parallelograms, that means two parallelograms which are on the same base and between the same parallel, then the area of the two parallelogram has to be equal. Okay, as you can see in this figure, we have a two parallelogram. First one is parallelogram A, B, C and D, and the second parallelogram is E, F, C and D. They are on the same base DC and lying between the same parallel line AF and DC. Okay, so these are the two parallelograms which are on the same base DC and between the same parallel DC and AF. Now the area of these two parallelograms has to be equal. That is, the area of A, B, C, D should be equal to the area of E, F, C, D according to theorem 9.1. Okay, so we are going to prove this theorem also. So let's start this proof. First we will write the given part. Okay, so write given. Given here is two parallelogram. First is parallelogram ABC and second is EFCD. Okay, given is two parallelograms ABCD and EFCD, which are lying on the same base, which is DC, and between the same parallel parallel lines are AF and parallel to DC. As I said, while mentioning the parallel lines, we will always mention the name with the on endpoints. Okay, so the endpoints here are A and F. Okay, to prove here is we have to prove that the area of the two parallelogram is equal. That is, area of parallelogram ABCD is equals to area of parallelogram EFCD. Okay, That's what we have to prove, that the area of two parallelogram is equal. Okay, so let's start this proof. When it's proof, what we are going to do is we'll be dealing with these two triangles first. Okay, triangle ADE and triangle BCF. In these two triangles we are going to prove that these two triangles are congruent. So if these two triangles are congruent, then their areas will be equal, and in both the area will add the area of this region, and we will get the required result. Okay, so first we are going to start with the two triangles. So start in triangle ADE and triangle BCF. We have what we have is the angle A. This angle A will be equals to angle B. Okay, that is angle DAF, sorry, DAE will be equals to angle CBF. The reason for this one is they are the corresponding angle. Okay, so these two are AD and BC are the parallel lines, and this AF is acting as a transversal, so these two are will be the corresponding angle. They has to be equal. Okay, so reason for this one is corresponding angle. Okay, in similar way, the angle E, which is angle AED, and the angle F, which is angle BFC, will also be equal. Okay, and angle AED will be equals to angle BFC. Again the region is same, which is corresponding angles. Okay, they are also corresponding angles. Okay, so we got two pair of corresponding angle. That means these two corresponding angles are equal. So by applying the angle sum property, the remaining angle, which is the third angle, angle D, and angle C, will also be equal. Okay, so I'll directly write, therefore the angle ADE will also equals to angle BCF. For this one is we are using the angle sum property. Since the other two angles are equal to each other, the remaining angle will also be equal then. Okay, so reason for this one is angle sum property. Okay, so since the two pair of angle is already equal in respective triangle, so the remaining angle, which is the third angle, will also be equal, because the sum of the three angle of a triangle is 180 degree. Okay, so if the measurement of the two angle is fixed, so the one will also be similar. Okay, so now what we got here is we got this angle A, which is this one, and we got this angle D, which is this one. Okay, now we'll take this their included side, that is AD will be equals to BC, because they are the opposite side of the parallelogram ABCD. Okay, so we'll write, and this side AD will be equals to BC. Side AD will be equals to side BC, because they are the opposite sides of parallelogram ABCD. Okay, now applying the angle side angle congruence rule, these two triangles will be equal. Okay, so we'll write, therefore triangles are ADE is congruent to triangle BCF. Okay, this is by angle side angle congruence rule. Okay, hence as we know, if two triangles or any two figures are congruent, then their areas will also be equal. Therefore we can say, hence area of triangle ADE will be equals to the area of triangle BCF. Okay, the area of triangle ADE will be equals to area of triangle BCF. Okay, let's name it equation number 1. Now what we are going to do is, we have proved that the area of these two triangle is equals to one another. Okay, now we are going to add the area of this shape in both the triangle. Okay, so we'll write add on adding the area of that figure is EBCD. Okay, area of EBCD on both sides in equation 1, we get what we get is, in equation 1 we have area of triangle ADE, and we are going to add the area EBCD to this, and that will be equals to the sum of the area of triangle BCF plus again adding this area, that is area EBCD. Okay, so when you add these two, you will get the parallelogram ABCD. Okay, and when after adding these two, you will get the parallelogram EFCD. Okay, hence the area of the two parallelogram is equal, and this is what we have to prove in the theorem 9.1, that the area of two parallelogram is equal if they are lying between the same parallel and on the same base. Okay, we have proved that the area of parallelogram ABCD and EFCD is equal. Okay, now moving ahead to the example number 2 of your NCERT textbook. Okay, which is given on the page number 158. This example is very important. Okay, so let's do this example. The question of this example is, if a triangle and a parallelogram, so what we are having here, a triangle and a parallelogram are on the same base and between the same parallel, then prove that the area of triangle, that is the area of triangle, is equal to the half the area of parallelogram. Okay, so if we have a triangle and a parallelogram which are on the same base and between the same parallel, then the area of the triangle is equal to the half the area of parallelogram. Okay, so let's see this figure. We have a parallelogram A, B, C and D. Okay, and we have a triangle which is A, P, B. For this parallelogram and the triangle, we have they are on the same base, which same base here is AB, and they are lying between the same parallel AB and this PC. Okay, so let's try the given part first. Given here is a parallelogram ABCD and a triangle PAB lying on the same base here is AB, and between the same parallel lines here are AB parallel to PC. Okay, what we have to prove here is, we have to prove that the area of triangle, that is area of triangle PAB is equals to the half the area of the parallelogram, which is ABCD. This is very important question. Okay, so this example number 2 is very important. That's why we are doing here. So what we have to prove here is that the area of triangle PAB is equals to half the area of parallelogram ABCD. Okay, so we are going to start with the construction. Okay, what we are going to do is, we will draw a line which is BQ, which will be parallel to the line PA. Construction is, draw BQ parallel to AP. Okay, we have drawn this line segment which is BQ, and this has to be parallel to AP. Okay, so with this, now we have two parallelograms here. First parallelogram here is ABCD. Second parallelogram is ABQP, and we know that the two parallelograms which are on the same base and between the same parallel, then their areas has to be equal. Okay, so we'll write the proof on the next page. Okay, so we have here two parallelogram ABCD and ABQP. Okay, proof is, since parallelograms ABCD and second one is ABQP are on the same base. Same base here is AB, and between the same parallel lines here are AB parallel to PC. Therefore, by theorem 9.1, the area of two parallelogram will be equal. Okay, therefore area of parallelogram ABCD will be equals to area of parallelogram ABQP. Okay, let's name it equation number 1. Okay, so we have used the theorem 9.1 here. Write the reason here. By theorem 9.1, or you can write the statement of theorem 9.1. If two parallelogram are on the same base and with the same parallel, then the areas will be equal. Okay, so by using the theorem 9.1, the area of the two parallelogram here is equal. And as you can see, for the parallelogram ABQP, this PB is working as a diagonal, and we know that the diagonal of a parallelogram divides into two triangles of equal area. Okay, so we have in parallelogram ABQP, PB is a, we have this ABQP, PB is a diagonal. Okay, PB is a diagonal, therefore the triangle PAB will be congruent to triangle BQP, as we know that the diagonal of a parallelogram divides into two congruent triangle. Okay, as we know, the diagonal of a parallelogram divides it into two congruent triangle. So what we have is a diagonal of a parallelogram divides into two congruent triangles. So therefore these two triangles are congruent, and we know that if two figures are congruent, then their areas will be equal. So the area of triangle PAB will be equals to the area of triangle BQP. Okay, so the area of these two figures will be equal, and we can write this as, when you add these two triangles, you will get the sum of PAB plus triangle BQP. When you add the area of the two figures, you will get the area of the parallelogram ABQP. Okay, because these two triangles are formed by the diagonal of parallelogram ABPQ. Okay, and we know that the area of this ABPQ is equals to the area of ABCD. Okay, so we can write in place of ABQP, we can write area of parallelogram ABCD CD. Okay, since the area of these two is equal, as it is given here, we can write this as twice the area of PAB. Okay, so what we did here is, since the area of these two is equal, so we can write this as twice of area of PAB. Okay, and the area of ABQP is equals to area of ABCD, as is it given here. Okay, so this, from here we will get area of triangle PAB will be equals to, this 2 will, when you shift it to the right hand side, will become 1 by 2 area of ABCD. Okay, and this is what we are asked to prove here. Okay, so that's what we were asked to prove here, that area of triangle PAB is equals to half the area of parallelogram ABCD, and we have proved this. So with that, we have completed the example number 2 and the theorem 9.1. Before the exercise 9.2, we are going to use this theorem and the example in the exercise 9.2. okay, so you have to practice this and in order to understand this better. Okay, so with this we have concluded this session. That's all for now. Thanks for joining here, everyone. Thank you.